there are two key words in the title, namely spherical functors and toric geometry. So in a way, the slogan here is that spherical functors are present in, and this is not new, of course, these days at all, but spherical functors tell us a lot about birational geometry in general. And since the, I guess, early 90s, this has been one of the themes that lots of people have worked on, and you know, in a way, one could say that it's one of the methods that appeared quite recently in such a classical subject like birational geometry. So one could say that I think it's still quite a bit to do. So there's still many things that perhaps people that we don't know, and you know, the method sort of has a lot of promise, and hopefully some future developments will still happen. And the reason for bringing the toric geometry story, as usual, is that, of course, one would ideally want to do something which is not necessarily restricted to toric varieties. However, we have this huge advantage in toric geometry that when we don't know something or we don't understand things very well, we can use the machinery of toric geometry, the combinatorics involved, and all sorts of things to do calculations. So that's the reason why, and surprisingly, even in this case, there are still many things that are not understood. And of course, symmetry is a prime example of that. People who do mirror symmetry know that whenever you have a new idea, you want to try it in the context of toric geometry. So let me start with, I'll try to write as large as I can. Is this legible in any way? Yeah? Okay. So let me just give first, as I promised, an intuitive categorical picture. So what so let's say one would start on what we would call the A side. So you know, we could start with superpotential. I'll call it W star for reasons that would be apparent very quickly. And then the sort of think that X star is a algebraic variety. And ingredient that's interesting in the story that I want to present is that X star is some kind of vibration. And for us, as I said, all of this is going on in the toric world. This is, you know, something that in the last, I don't know, 10 years or so this concept has appeared in lots and lots of discussions in mirror symmetry. So somehow, if we think from the point of view of A side, what wants to do, it wants to do a push forward some kind of Fukaya category associated to this, which could be also a Fukaya-cidal category, and then study Fukaya category with categorical coefficients. So this is an idea that I think, not surprisingly, that appeared maybe for the first time in a talk by Poncevich, and since then it's been expanded and in many contexts. So what is interesting here is that in the base there is a discriminant I'll call it now for now delta, or actually let's call it lambda. Where the fiber-wise probably I think here we would have to take some wrap version. Category of the fiber, let's call it X star A, degenerates. And then the question is, how do we understand this family of categories with this degeneration? So this is in category theory, this is a notoriously difficult problem. And again, that's where this development by Kapranov and Shechtman, maybe also like 10, 15 years, maybe more than 10 years by now, happened, that this idea of the appearance of a Schober. So I'll just write here the name. I will avoid using this name. So Kapranov, Shechtman. They were the ones that sort of maybe I'll mention it a bit about this a little later. So they were the one who kind of formalized this in various contexts. By now, there are again all sorts of examples of even on the A side where this is understood, and you know, people have done all sorts of examples, worked out all sorts of examples. But my point of view here is in a way different, and it's on the B side. So the B side, at least in this context, has been studied, of course, a lot, and everything I'm going to say has been studied in many contexts. But at least in this sort of has not been studied that much. So again, the question is understand the behavior of, so say again, X is some algebraic, right? Some or stack. Usually we're going to work here with the Mumford stacks. Understand that Jaeger bounded derived category of here a sheaf on the fiber, and again try to understand this as its behavior around the discriminant. So this again is a very classical problem from the point of mirror symmetry, and even in the, I guess in a way the first paper in mirror symmetry, well, that at least the one that caught the attention of mathematicians like Candela, also Green and Parks, the sort of this, in a way, if you try to understand what's going on there, a lot of it has to do with exactly trying to understand the behavior of this system of the system of PDEs around the discriminant locus for that example of the quinting. So, okay, so now, so the ingredient that is needed here turns out to understand how the interaction between, and I'll put here the words, so the interaction between, in the context of perverse sheaves, say the interaction of what's going on when you approach the singular locus is the so-called formalism of nearby vanishing cycles. So this formalism is sort of precedes this discussion by maybe 15 years. So there's this famous book by BKK, right? Or by Bailinson. I'm gonna be in trouble here, but the Lean and Bernstein, I think. And so that's all worked out there. And it turns out that what Kapranov and Schickman noticed, that this has to do a lot with the notion of spherical functors. So at this level, it's just an analogy, but I'll try to say a few words about spherical functors here. So this is a notion that is being, at least I became aware in talk by, I think in by Kontsevich, maybe 97, and then Seidel and Thomas wrote a beautiful paper where they kind of developed the theory, wrote the definition, and they sort of developed this, at least up to some point for some example. So the notion that the categorical notion was then formalized by Anon Logvinenko. So that's the there were all sorts of versions of spherical functor with different names. I had a contribution here where I call them easy spherical, which is a sort of basically it's a Seidel-Thomas functor in a family. And then based on all these developments, Anon Logvinenko came up with a nice abstraction of this. So, so the functor F, say C and D are DG categories. Probably by now there are all sorts of different versions, but more general. But this is L, this is R. So the left adjoint, the right adjoint. So S is spherical. If I'll write the formal definition, which I can never remember here, but I'll write it if, because it looks weird, but that's by design. So T, which is the cone of this junction, is an equivalence. And two, there's a more technical definition and composition. R RSL. So these are all natural maps. P1L plus 1 is an isomorphism where I have to say what T1 is. T1 is the cone, the analog of T for the other adjunction I. So,
well, this is the bracket.
This is the cone.
Yeah, but down there.
Here?
Of what?
Plus 1.
Oh, it's
The shift by 1, right? P1L shifted by 1. So, of course, this is in a way, a crazy definition. So the remarkable thing is, and that's the reason I wrote it. The remarkable thing is that it seems to be the natural thing, and the T, the induced autoequivalence T is called the spherical associated to S. And let me, I guess there might be someone here who doesn't know where this name comes from. So the example is let's say X projected Calamiel. Then one could take the following functor from the category of graded vector spaces. So let's say this K goes into OX, and this is spherical. So and the induced twist is the cone over the restriction from to the diagonal of the structure sheaf on X cross X. So induced twist is the Fourier unified functor defined by this object. So now maybe it's a good moment to say a word or two about this, since this actually will play a role, hopefully, will play a role in what I'm going to get to say this. But in mirror symmetry, for those of you familiar with the SYZ conjecture, the SYZ conjecture states that there is a duality, T-duality, ideally for any two, say, projected Calamiels, let's say threefolds, where the basis is an S3, and you sort of do some T-duality, and then you compactify in the right way, and that's kind of captures geometrically mirror symmetry. Of course, we now know that things are not so simple, but what I should say is that the reason why this is called spherical is that this OX here, from the SYZ point of view, is supposed to mirror this S3 based off the SYZ privation on the other side. So in this, so it is something special about this self-equivalence, namely that it really captures a very important twist, and then the associated mirror twist is going to be a Dan twist, generalized Dan twist, or sometimes called this a sidle Dan twist, associated with S3, at least in the, as I said, in the threefold case. So
just have a very basic question.
Yeah.
So could you just remind what is the formula?
oh, the cone. Oh, well, this is a triangulated category, right?
Yes.
So you just close the triangle, and the cone is the third object in that closes the triangle, right? So in this case, I guess it's going to be the ideal sheet.
Right, and then, but you say it's an equivalence, so it's an equivalence of,
Is the creative right?
or you take the three amount
Yeah.
of that.
Right, of this order.
I see, I see.
Essentially, it's the ideal sheet of the diagonal.
Yeah, I was confused. Yeah, I see. Thank you.
Okay, so so what do I want to do? So this is kind of the, as I said, one of the actors in the story is this spherical functor. It's still not clear yet what is the connection with, not clear at all, what's the connection with the birational geometry. And as I said, it seems to me that one context when this can be understood is this toric geometry. So I'm going to just go briefly over a few notions that are needed here, and of course a very biased point of view. Do you know what time did I start? Kind of approximately.
So what time did you start?
Yeah. Do you know, Joseph?
I think it was about 3 and 10.
Okay, good. So I'm going to start with what I call a set. There are various. So it's a bunch of vectors in a lattice. And then I'm going to introduce some notation. So let me call K. Or maybe I should say that the reason it's called an A set is that there exists a homomorphism such that, so the hyperplane condition, also all the VIs would sit in a hyperplane, and of course I should say that this is almost everything I'm going to say today is contained in this famous green book, at least at the combinatorial level is contained in the green book by GKZ. So let me, so I was going to say that I want to introduce the notation K for the cone over these vectors, the convex hull of them, called Q. And so in order to talk about the birational geometry, I have to say what are the toric varieties that we're interested in. And so there, it turns out that you can naturally associate two of them, two toric varieties, rather, I would say that toric stacks, but we don't have to worry about too much about that here. So one of them is to do something that people do all the time. If you take the book by Fulton, say, and you look at let's say we work with over C. You take the dual, and spec of this, and it turns out that this hyperplane condition, so this is a affine toric Gorenstein singularity. So it is bad, but not so bad. It can be pretty nasty, but still manageable. And again, without the hyperplane condition, life is more difficult. One these days, of course, work with that too. But here we're not going to worry about that part. And the second and more traditional way of getting a toric variety is from this is to take consider fan, let's call it sigma, and let's say a simplicial fan for now. Sigma supported on K with vectors generated by the VIs and this is the usual yoga that people do. You take a fan and then you associate with the Riemann for set. And for all intents and purposes, for in this story and in this talk, this is a preferent resolution of Y. As I said, with the caveat that when I say resolution, I do have to think in terms of stacks. So of course the magic here is that that's where the combinatorics story comes in. That you can change this stack structure by changing the. So then you could have different. So I'm gonna skip the term. Usually you write this as Koch to show that we're talking about coherent sheaves. And it turns out that these for different stack structure, these are equivalent. And this is this famous and classical story which goes back to Bondal-Orlov, then Kawamata, and many other people. So this is going to be a sort of a sequence of flops that one can explicitly write down examples. Okay, so I need one more actor. Then I'm just going to jump in to, as I promised, I want to say something and present some results and conjectures. So there is one more actor that we need, and namely, and this is also due to this GKZ A discriminants. And so we all know what that if I take what the classical discriminant is, so I can write something like a polynomial like this. I guess so. It's a Laurent polynomial. So so the discriminant is the irreducible polynomial in. So it lives, I guess, with integer coefficients that vanishes at y in C star to the D, I guess, such that f is singular at y. So this discriminant is going to capture exactly the discriminant that I was talking about in the beginning as sort of being living in the base of this categorical vibration. So as I promised, one more important factor is this object called EA, which GKZ call it principal A determinant. You want to know the name, the reason for this name, should ask them, I guess. So it looks like this. It's a product over, I'll explain in a second, over so there are a few things to explain here. So gamma, so these are all the non-empty spaces. So non-empty space of Q. So what you do, you take the intersection of the set A with a corresponding face, and you write down the discriminant. I could say that the discriminant, if this is not a hypersurface, by the way, the discriminant, and that's not classically true, is 1. So it may happen that not all the faces give proper proper terms in that product. But you know, the interesting ones where the geometry happens are going to give proper components, and there are some coefficients here. So I of lambda is, I'll just write the words. I of lambda is the index of A intersected lambda, the lattice in N intersected lambda. You sort of, you know, basically it has to do with the torsion of U1. And U of lambda U of lambda is the following thing. So what you do, you take a projection of the lattice n onto the quotient lattice, and the quotient by the lattice generated by and then the image of the set A is not going to live in a hyperplane anymore. So I'm just going to again draw the picture without writing any formula. It's going to be, you know, a bunch of, and what U of lambda is the volume the red volume of this picture. So these are the images of the I, where here the I, those ones are the I. And right, so in a way, what everything that's at least at this level of if I want to be kind of to make this a highbrow, give a highbrow to what I'm going to say, one could say that what we're going to do here is some sort of try to do a categorification of EA. More precisely, every numerical information we're going to get is going to be sort of encoded into this EA. And the sort of game that we play is sort of lift this at the category level so that this is consistent with the numerical information. And the people who have tried this in many other contexts know this is more like more of an art rather than a science, and they're the same problems arise here too. So let me now. So these are as I said, the actors. So now I can, as I promised, I can write down some numerical results first.
And so what is the meaning of this EA? Like in a usual.
Oh, yes, that's what I was gonna say. So exactly. So you may say, hey, what's up with this EA? Why would you bother to deal with this EA? And because if you perhaps have done this as a project in high school or earlier, I don't know. When you play with the discriminant, when you first learn about polynomial, you play with the discriminant, and you get this horrible expression. You can't learn anything out of it. So this is a problem that people have tried from, I don't know, from 600 years, trying to solve polynomials and all that. So they were masters in doing this. So it's kind of remarkable that in the 90s, Zelensky came out with this polynomial, and what you can say, you can actually say exactly what the Newton polytope is of this principal A determinants, which for the classical discriminant is something impossible to do. So now somehow what they did is so this is the second polytope associated A. Or for those of you who are more familiar, is the dual polytope to the secondary fan. Okay, so what is and so that's why this is quite a remarkable construction. As I said, there is, classically the discriminant, it's a unpleasant mess. Somehow, by doing this, they had their reason, so to speak. So let me just say, so let's call this secondary of A. So what is this? Is the convex. So this is kind of a very cheap definition. It is a definition, but it won't say much. Is the convex hull of the characteristic functions. So sigma is a one of those dm stacking fans. So for each of them, you build this so you take characteristic function, of course, on the vertices. It works like magic. If you try it, it's kind of fun. You haven't done it at all. And you take this, for each vertex, you take all the maximal simplices that contain that, and you add the volumes. You can think about this as living naturally in some kind of vector space with R to the n, I guess. And you take the convex hull of this, and this is the secondary fan, as I said. Polytope. And it turns out, as I said, that this is the Newton polytope. There you see. Of the. So maybe now it's time to say a few more words. So in fact, they do much more in this work. They also can characterize what some of the, you can calculate some of the coefficients of this polynomial, and they have to do with the volumes, and you cannot, there's no known recipe for calculating all of them, but you can certainly, in some kind of asymptotic limits, you can certainly calculate what these coefficients are. So now, so this is the machinery. So let me now write some results and some conjectures. So the idea is that, so I'll remind you now what the, maybe I'll say just the words. So the idea is that the discriminant, right, has, so this basis of this categorical vibration has a bunch of components, and in principle, they're in one-to-one correspondence with all the faces of this polytope Q. Right? So what this, as I promised, what we're trying to understand, besides the fact that we know that we have this birational equivalence on the smooth part of the locus, what we're trying to understand categorically is what happens along these components. So the theorem, this is kind of I think it follows from various, I don't know if it's stated anywhere, I mean it's stated in our paper this way, but it's probably sure it's somewhere written down. So for any edge f of this secondary polytope, there exists a spherical functor where the f is, the important thing is a toric, the limb for stack, associated to f. So you give me the edge, and I'll hopefully I'll have time to show an example. So you give me the edge, I'm able to to understand, to build this stack Zn. And by the way, here there is this huge topic of one way to understand this functor is this through this method of using windows, which I'm not going to say anything about in this talk. So so now what got us to look at this, in fact, well, besides being, maybe I'll erase here, is this conjecture by through some kind of string theory considerations by Aspinwall, Plesser, and so Aspinwall, Plesser, and Wang, 2017, I think. And what their conjecture is that there exists for each phase gamma of Q, there exists a spherical functor of the type EB. I'll call it here Z gamma. Where Z gamma again is the limb for stack combinatorially defined by the fan sigma and the corresponding phase gamma. So the way you should think about this functor is that, again, you have a component here of the discriminant. Along the component, there is this category. This is all sort of wishy-washy because it's not, can't really talk about families of categories along discriminants, but the idea is that you should think about it as in some kind of moduli space of stability conditions that this corresponds to a spherical functor. So this is a picture in, if you want, in stab of X sigma. This is a point here corresponds to a smooth X sigma, and it's exactly this the corresponding the sort of mirror picture to the Picard-Lefschetz, if you want, and the story about vanishing cycles and all that. So there is more to this story. There probably is some, not probably, definitely, there is some wall crossing inside the discriminant. So when you move, in fact, along the discriminant, the category will not change. However, the actual spherical functor will change. So that's something very interesting, which we haven't gotten doing, but it's kind of an interesting project. It might be a little bit related to, so one aspect that I'm completely ignoring here, but it's always in the background, is this story about the quantum D module associated to this picture, and that's kind of the guiding principle, if you want, for many of these calculations. So the conjecture we have a bunch of conjectures. I'm going to be brave, and maybe at least the last one should be more like a speculation, but I'm still going to maybe write it as a speculation. And this conjecture implies the APW conjecture, is the following, that for any edge F, edge F of the secondary, there exists a semi-orthogonal decomposition of the category associated to the edge into n gamma F components of dBz gamma for each gamma. So in other words, what we're saying is that this dBzF can be decomposed in a bunch of components of the form dBz gamma, and we can count precisely. So this is some asymptotic multiplicity, which can be computed by looking the right way at this principal A determinants. So the numerical theorem we have is the following, and to justify this, is that the rank of K0, I'll write here of ZF, where is the sum of n gamma f of the rank of K0 of the Z gamma. So again, the proof here is asymptotics. In fact, it's very so asymptotics just a calculation and sort of looking carefully and doing the two sides of the definition of EA, kind of giving the right interpretation in terms of rank. So I think I have 5 more minutes, maybe. So now let me the conjecture, which is true. I'm not sure, they might need some extra conditions, but in general, but in fact, the conjecture is in fact that the first type of, there is an analog of the first type of spherical functor. So there is for each face f of the secondary polytope. There exists a spherical functor of the type dB of GF where ZF again is a Deligne-Mumford set. So maybe I should put here speculation. For people familiar with the spherical functors, they're notoriously hard to deal with. So proving this would be kind of this would, at least in principle, this would offer new examples of spherical functors, which are not that many. If you look in the literature, there are not that many new examples for the last, I don't know, 10 years or so. There haven't been, at least in this context, many examples of this. So yeah, I should say here the asymptotic. This is kind of what I was gonna say. I didn't write tropical in nature. Tropical in spirit. The argument, at least. It's kind of doing away tropical geometry. And then we do have the numerical version of this, but it's not clear what it means. So I'll write it, This is why this is a little probably wishful thinking. But that's again just a tropical numerical result. So it says that the rank of A0 of this ZF times. So now I have to take the Newton polytope of some discriminant polynomial associated to the face F is written as a sum again of the ranks of these Z gammas. But now here I get again Newton polytope of some. So certainly what this formula says is that in general, we cannot hope to have an analog of the previous result where for an edge, we have a semi-orthogonal decomposition, unless there is some kind of story behind this formula, which I don't understand exactly. So, so before, so I want to, I have a file here that I would like to project. Just let me show you one example. Some of you may have seen this example, but I'm still want to. Some of you may have not. It's my favorite example, in fact. Okay, thank you. Just 2 pages. So this is in a way, you can call it classical, but it goes back to these when string theorists started doing mirror symmetry and started doing calculations. They were looking at this example. So you start sort of with F2, Hirzebruch surface, which you can think of as a resolution of P112 or P211, as I wrote it there. And then the ambient Calabi-Yau that we're going to work with is the canonical bundle of this, so the total space of the canonical bundle. And it's what's called on this picture, the combinatorics is captured by what I call the X1. So it's a Kreppen resolution. We're in good shape. And then combinatorially, this there are only 4 ways to triangulate this picture. And geometrically, you see the lower left corner is C3 over Z4. So this is kind of the so-called Landau-Ginzburg model that Anatoly had in the one-dimensional case before. On the lower right, that's kind of the total space of Stacky canonical bundle over the Stacky projective space. So there's a variety, has some similarities. And then the upper left corner is it's interesting because that's kind of the hybrid model that Anatoly was alluding to, and I asked him about. So, and the pictures are here. So S of A is the secondary polytope in this case. And, you know, I also mark, you see, the edges correspond to some polyhedral subdivisions. I didn't talk about this at all, but you see there are some markings there that tell you that that is not a triangulation, it's a marked polyhedral subdivision, and they correspond to what I call their F14, F23, the transitions. So, oh,
I have a laser, yeah, right here.
Oh, oh, good. Okay, I can go back, right? No, okay. Okay, so this is kind of yeah, the marking. This is going to correspond to this edge combinatorially. And now, if you can, okay, thanks. Okay, so this is. As I said, behind this, all this machinery, so that's why I wanted to show this picture. There are computations with monodromy and you know, some linear PDEs, kind of, you know, unpleasant. You try to do them in higher dimension, even for this example, they're actually unpleasant, in fact. So here the discriminant has the interesting components are this d delta corresponding to the whole to the full polytope, and there is gamma. Gamma is there is only one edge, which from the point of view of this story is not simplicial. There is a point in the middle. So that's the component corresponding to gamma. And then one can analyze, you know, so this is kind of the guiding kind of principle here. We're moving in this moduli space of complex structure. That's what I have in mind. And we're mimicking this picture by trying to understand what's going on at the level of birational geometry. And the reason I wanted to show this interesting, as I said, there is some kind of wall crossing here. You see, if you So the discriminant, this component is exactly given by, I think it's y equals 1/4 in these coordinates, doesn't matter that much. However, so the loop corresponding here, of course, you see from the picture, right, that if you take a loop here, this is going to be the mirror geometrical picture of the spherical functor is going to be this one. X1 is the ambient variety. However, if you go on this side, and you take a loop, sort of, so the K now is, well, large, I said, and you're going to get a very